All right. So last time we talked about the sort of the messy mathematics behind the spectrum. So we started with a spectrum and drilled down and we got to the wave function. Okay. And we saw that the wave function was everywhere. The wave function is on the horizontal axis because the horizontal axis in a spectrum is the differences in energy levels, maybe converted to wavelength or whatever. But we have a transition that goes from energy level 1 to 2 or 2 to 3. So those show up at different positions. Those energy levels come from the wave functions using Schrodinger's equation. So Schrodinger's equation in your mind should be connected to the energy levels. It operates on the wave function and gives us those energy levels. Okay, but then the y-axis, the vertical axis of the spectrum, is also related to the wave function because we have the initial wave function and the final wave function, and it's interacting with light, and we're modeling light with the x-axis, or the x-axis squared if it's a scattering situation. So, but we still have the wave functions there too. But I just showed you the wave function last time. I didn't develop it. But anyway, in terms of the spectrum, the wave function is key to everything. Now, with science, we kind of backed into this. We had the spectral effects, and we couldn't explain any of it because we didn't know about wave functions. So in quantum thinking, they struggled with this until de Broglie came along and said, what if nature's behaving like discrete waves, standing waves? And this idea, Einstein thought had merit. He handed it off to Schrodinger, who solved all the equations. So it was de Broglie that came up with the idea of waves, and Schrodinger did the math. And so it's really though still just a postulate. There's no way to prove this because we can't see the wave functions. We can't get in there to see if they really exist, but the math works. The math is able to predict the spectrum very well, but it's still, this idea is a postulate. A postulate is something that's assumed to be true. We can't really prove it. It's a starting point. So this lecture is about the postulates of quantum mechanics. There's 4 or 5 of them. Okay. So we're going to go through those postulates and expand upon them. One of them is about the wave function. But it was just this postulate. So de Broglie, you could say, de Broglie postulated that nature behaves like waves. And then with that assumption, we were able to turn it into spectroscopy. Okay, and it matched the data. So in mathematics, it's an assumption used as the basis for mathematical reasoning. So part of the I think maybe some of the mental tension that you feel when studying quantum mechanics is you don't necessarily understand why we're talking about waves and everything. And that has still never been explained because it's a starting point. We're starting with the assumption that nature behaves as waves. So no problem if you feel a little uncomfortable with that. It works really well, and so that should make you feel better about it. But as far as whether these waves really exist in nature, we can't say. It's just a starting point. I'm a realist. I think they do. But other physicists say it's irrelevant. It's a dumb question. They call it the shut up and calculate people. They're like, I don't get into metaphysical questions about whether the nature is oscillating like a wave. I just calculate and it matches my data and we're happy. I don't get into the deeper questions about do they really exist? Okay. So postulate number 1 is the state of a quantum system can be completely specified by the wave function. Notice that's not a conclusion. That's de Broglie's postulate. He's saying, what if? Let's just start with the wave function and describe it. And this when refined, we're saying, yes, the quantum system can be completely described by the wave function. And there are some other parts to this postulate. Like if we take the square modulus, it really looks like just the wave function times itself. But if it's imaginary, we have to do the complex conjugate. Everywhere there's an I, we change the sign. But we're not really going to get into that. It's called the square modulus, but you could say the square of the wave function is the probability distribution. So this is the probability that a particle will be found at an interval dx at a certain time. Okay. And so then if we integrate over all space, we've looked everywhere, then we have a probability of 1 of finding the particle, right? If you lose your keys, what are you going to do? You're going to look everywhere. You're going to integrate over all space. and if you haven't found it yet, that's telling you haven't looked everywhere. So, yes. So in our one-dimensional system, which is very nice, we just have dx. If we had x, y, z, we'd have a triple integral. And if we look over all time, we'd have a quadruple integral. And so we could do that, but let's keep it simple. Let's just keep a single dimension, the x-axis. So we're only concerned with one dimension, thank goodness. Okay. So there are invalid wave functions, things that don't match the math and also don't make sense from nature. Okay, so we can't have a wave function break in the middle because that's not continuous. We can't have a wave function that has a pointy piece. So this is this sharp point here. Says that the first derivative is not continuous. So the first derivative is the slope, and so if I were to plot here, let's see, I don't know how to plot this. There's not enough room. But look at it. If I'm coming at it this way, my slopes are all positive. You see that? So at this point, my slope is positive if I came at it from the right. But if I came at it from the left, all these slopes are negative. So when I get to that point, my slope is negative. So at that point, what's the slope? It's not defined, right? It depends on which direction I'm coming. So we can't have any sharp points on our wave function because Schrodinger's equation makes us take the second derivative. And so if my first derivative is discontinuous, I can't take the second derivative. So we can't have any sharp points on our wave functions. They have to be smooth. It can't be double valued, or multiple valued. So like right here, this wave function has 3 values at x, at x1, if you want to say. And so it can't loop back on itself like that. And then here, it's not finite, it goes to infinity. So the area under this curve cannot equal 1. Not equal to 1 if at any point the curve goes to infinity and I try to take the area under that curve, I'm going to get infinity, not 1. And so it has to be normalizable. It has to have a finite area under that curve. So it can't diverge and go to infinity. So these are hard requirements. You see the little homework symbol on there? These are things that I try to put those on there so that you can get a clue, a quick find whenever you're doing the homework. So they must be continuous. That's basically everything I've said. So now let's build a wave function for a particle in a 1D box. Now there are certain functions that oscillate, like sine functions, cosine functions, and e to the x, which is really like a sine x minus I cosine x, or whatever, the Euler's relationship. So e to the x is also an oscillatory function. So let's just start with a simple one, sine x. And let's plot it. Let's say that our box length is 7. So we'll do 7 angstroms for our box length. So we're going to plot sine x from 0 to L. So 0 to 7. So it's nice. It's continuous. So it fits that. It's finite between 0 and L, so it doesn't go to infinity. It has a continuous first derivative. It's smooth. It doesn't have any sharp points. Okay, but look over here on the right. It doesn't go to 0 over here on the right. Okay, so it's not 0 at the boundary. That wasn't one of my original ones. Okay, but if this is a standing wave, at the boundary it needs to go to 0 for it to be a standing wave. Okay. So this boundary condition is a new thing that we've put on our wave function. Now, if it was at 6.28, it would be a good. If our box was 6.28 angstroms, then this would be fine, okay, because it's 0 at both ends. But because our box length is 7, it's not good. So somehow we need to scale this based on the box length. Okay, so let's take x and divide it by L. So now it goes from the sign of 0 to 1. So x is 0, and then when it gets to L, we have L over L, which is 1. So this is 0 to 1 inside of x. But the sign, 1, if you take the sign of 1, it's not 0, but the sign of pi is 0. And so let's take this scale 0 to 1 and multiply it by pi, so that we get a pi piece of the sign. It goes from 0 back down to 0. And so this scales it now to where when we go from x equals 0 to L, when it gets to L, it cancels out with the L, and we end up with the sign of pi, which is 0. Okay, so this is great. Now we have a good wave function in terms of it being 0 at the boundary. So it's finite between 0 and L, it's continuous first derivative. Now it's 0 at the boundaries. Okay, but it's not centered on 0. And I'm a symmetry person. I want my wave function centered on 0. Okay, so how can we shift this around? Well, we want to add something to x. In fact, we somehow want to add 3.5 to x, which is half of L. Okay, so we can add that pi over 2 inside here, and that will center it on L. So now our wave function satisfies the first criteria. It's also 0 at the boundaries, and now it's centered on 0. But it doesn't have any quantum numbers. And it's a quantized system, right? We want to make sure that if we increase the energy, it'll have more curvature and so on. Well, we can't do that. We have no variable in here that would be the quantum number. And so let's put the quantum number in. So now we have finite wave function. It's continuous, it's smooth, 0 at the boundaries, it's centered on 0, and it has quantum numbers. So that's beautiful. So that's what this piece did. This piece right here is a phase shift piece, and that makes it centered on 0. Okay. And that's the piece that's in my wave functions that's not in any of the textbooks. So if you're looking up the particle in a box, or you're Googling it or whatever, you'll get the wave function, and it won't have that phase shift piece. So that's the difference between everybody else's and mine. Now this wave function, when we square it and integrate over all space, should have an area equal to 1. Okay? But there's a problem. The maximum of the wave function is already 1. And so if we square it, that's still 1. But then we're going to add all this other stuff. It's going to make it greater than 1. So we need to divide this wave function by something. We need to shrink it down and normalize it, so that when we square the wave function, the area under that curve will equal 1. Okay. And I've shown you here the wave functions for n equals 1, 2, and 3. So it's basically what I just said in text form. So if the wave function is already 1, if we square that, then we have other extra bits we add in on the integral that's not going to equal to 1. So you can show these waves with a slinky. Maybe we'll do that next time. So let's look at this square of the wave function integrated over all space. This is where we get into calculus. So when we integrate this over all space, we're using Dirac notation now. So you see this dx and the integral have gone away, and we get these angle brackets. Same thing, okay? And when n prime equals n, in other words, you're taking a wave function times itself, we end up with 1. And when you have a wave function times any other wave function, so like 1 to 2, then it's equal to 0. So we don't want our wave functions to be sums of the other wave functions. We want them to be independent. Okay. And so in one statement, we have this Kronecker delta, and we'll look at that later. But we see this when we do a numerical analysis, and you guys do your projects, you're going to see this result of this integration of every wave function times every other wave function. So this is wave function 1 times wave function 1 integrated over all space, and the result is 1. But if wave function 1 is times wave function 2 and integrated over all space, the result is 0. Times 3, result is 0. Times 4, result is 0. So if these are orthogonal and normal. So it's the condition called orthonormality. Normality means it's normalized, and that's the diagonal. And then the orthogonal piece is all the off-diagonal stuff, all the zeros. Okay. So let's normalize our particle in a 1D box wave functions. So here's our integral. So we have, notice here, n. They're all the same n. There are no n primes. So the arguments inside the sine functions are exactly the same. So we could say this is sine squared of all that stuff. And this is a constant n, this normalization constant. That's what we're trying to solve for. We don't know what that is. It's something that's going to multiply by the wave functions to bring them down. Right now they equal 1 or minus 1, but we need to shrink them down to where they're less than that so that when we square them and integrate over all space, that is equal to 1. Okay. Because the square of the wave function tells us the probability of finding the particle at a particular position in this box. And so we can't have any spot equal 1. The area of all that whole probability has to equal 1. So we need to solve for n. So we can combine all this. We bring the n out front, so it's n squared, and we have sine squared. Now, I like to make things easy, and I don't want to have to memorize the integral and the derivative of sine squared, cosine squared. All of my little pea brain can hold is the integral of sine or the integral of cosine. Last time we did the derivative of sine, and we found that it was cosine. And we did the derivative of cosine and found that it was negative sine. Okay, so we can do the derivatives. The integral is just the opposite direction. Okay, so if I have the integral of sine, it's going to be minus cosine. Okay, so did I do that right? Check me. Okay, so then we're going to do this. What can we do? So we want to get rid of this sine squared. So one way to reduce the power of an oscillatory function is to find a trigonometric substitution. So we go look through the tables, and I remember when you were in calculus, you probably had to memorize these substitutions, but we're not into that anymore. So just go find sine squared and find the trig substitution for that, and here it is. So it's the half angle formula. So sine squared is equal to 1 minus cosine of 2 times u, whatever's inside the sine piece becomes doubled, and then we divide everything by 2. So that's what we end up with. So this is implementing this substitution. Notice we have a 2 here, and then it was 2 over 2, and so the 2's are gone over here. Okay? And then we have the 1/2 out front. This piece shows up here and here, because this is 1 right here. So we have now 1/2 minus 1/2 times the cosine, and then we've doubled everything on the inside. Everybody cool with that substitution? Now we have 2 integrals. We've got the integral of 1/2 dx, and we have the integral of 1/2 sine, cosine something dx. So we'll break it into 2 integrals. So this is one of the easiest integrals you've ever seen. Okay? The integral of dx is going to give us x. I can do that, calculus. Right? And then the integral of cosine, I've memorized that, right? So we can do that too. So we do these integrals and we evaluate them at the upper and lower limit. These are definite integrals. They have the whole length of the box, a plus minus L over 2 and minus L over 2. So we have these evaluated at L over 2 and minus L over 2. So the integral of cosine is sine. And then we take whatever's in front of x. So see, this is in front of x. We don't care about this piece because it's times x to the 0 power. And so we're not worried about that. But this is times x to the 1. And so we're doing the antiderivative. And so we're going to bring this out front and flip it upside down. So this comes out front, and we end up with the L over 2 in pi. Okay, and there was already a 2 out there. And so that's where it became 4. Okay, is everybody fine with that integration? And then the cosine integral became sine. and then it's evaluated at L/2 and minus L/2. So let's put those in. So let's break it all out so that this x piece comes down here. We have L/2, and then we have minus L/2. And then this L/2 goes into x, wherever x is. So we have this L/2. Notice this is nice. That L cancels. This 2 cancels. And we end up with n pi plus n pi. Here the L cancels. The 2 cancels. And we have minus n pi plus n pi. So this whole thing becomes 0. Okay? So let's simplify. These 2's were multiplied by each other. The minus signs cancel. So we have these 2 pieces plus each other. And then we have this sine of 2n pi and sine of 0. So this is something you probably should memorize. The sine function looks like this, starting at 0. Does everybody recognize that? What is this? This is pi. This is 2 pi. Right? It goes through one cycle every 2 pi. This is 3 pi. This is 4 pi. So every integer multiple of pi, sine is 0. Okay, so what do we have here? We have a quantum number. Quantum numbers are integers. And so every one of those is going to be an integer multiple of pi. So we don't care what our quantum number is. We know it's an integer. And so all of those sine pieces are 0. And then over here we have sine of 0, by definition is 0. So all of our complicated stuff in this integral is gone, and we're left with a really simple equation that n squared L/2 is equal to 1. And we can solve for n squared. That's the square root of 2 over L. So we've normalized our wave function. This is the piece that goes in front of our wave function to make sure that when we square it and integrate over all space, it's equal to 1. And so now, notice our wave functions don't go as high as they used to because they're multiplied by this prefactor, the square root of 2 over L. So you can see now it's normalized. Okay. Because this was, in the previous page, this was n, the capital N, the normalization constant. All right, so we've done a little calculus. It makes you feel good. Gets your muscles going, your little brain stimulated. Yeah, okay. And so this is the first 3 wave functions. If we increase n equals 2, n equals 3. Now I've bounced them up based on the Schrodinger equation, the energies that come out of that. We haven't solved that yet, but we will here in a sec. But I just wanted to show you these wave functions and how they look. Notice as they go up in energy, they get more curvy and they have more nodes. Nodes are where it doesn't appear to be changing. So like right here. So this wave function oscillates up and down like this, like a standing wave, just like a violin string. These are the squares of the wave functions. Notice, look at n equals 2. This was a negative piece here. This was negative. This was positive. Now, not negative and positive in terms of charge. This is an electron, so it's a whole negative. But in terms of its oscillation, if we take a snapshot, it's below the middle line and above the middle line. You know, when we draw p orbitals, we shade them, right? It would be a red region and a green region. That's what we're doing. We're shading these different colors. So you might be able to shade this one a certain color and not shade the other. And so it'll be shaded on the right and not shaded on the left, or vice versa. Okay. And up here we might shade this one. So it's shaded in the middle and not shaded on the outside. And sometime later we would flip the shading. So when we shade our wave functions, that's what we're trying to capture, is the oscillation direction or where it is relative to its average position. Yeah. So now we're going to shade everything because this is we've squared it and we're integrating that shaded region. And integrating over all space, that shaded region, the integral of it all equals 1 now by definition, because we have. Now let's look at the first 10% of the box. This is where we start to see quantum effects. You know, if you say, think about it. If I put a pebble in this, well, it's maybe bad because of gravity. let's drop a marble in this box and shake it around. It has an equal probable chance of being anywhere in the box, right? So if we stick an electron on this wire and it's a classical electron, like a little ball on a wire, it is equal probable. If I integrate the first 10% of the box, I should have a 10% chance of finding it. That makes sense? If it's equal probable along the whole wire and I integrate the first 10% of the box, I should have an integral result of 0.1, 10%. Okay? I don't though. Look how little this is. So this is a quantum effect. If I integrate the first 10% of this box, this is what I get. I get a probability way below 0.1. It's like 0.05 or something like that. And then the next one, if I integrate that, n equals 2, I get a little bit better. N equals 3, it's a little bit better. But look at that oscillation. That oscillation in these integrals is what we would call quantum effects. It's the non-equiprobable distribution of that electron on this box. But what happens when I go up to quantum numbers? So these are all the integrals. I did all these in Excel. N equals 1, n equals 2, 3, 4, 5, 6. It even goes more than 10% up here. 7, 8, 9, 10, 11, 12. So this was, let's see. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is 20. This is 30, 40. So when I get up to, n equals 40, it's really starting to look classical. That in the first 10% of the box, I have a 10% chance of finding the electron. And so that's what we see when we get higher and higher quantum excitation. It starts to approach the classical value of equiprobable position in the box, if you will. And we see that with all kinds of systems. And then notice that there's really no smooth transition to the quantum effects. They grow in as you get smaller and smaller. Okay. Any questions or comments on this? Okay. Now let's look at the orthogonality. Okay, this one's a little trickier because, look, we have the sign n prime. So now we can't make a sign squared. Okay, so what are we going to do? Well, we find another trig substitution. Okay, so now I have, I pulled the 2 over L out. There was 2 of them, so when you multiply them, the square root goes away. Pull that out of the integral. And now we have a sine n times the sine m, if you want to, sine of 2 different arguments times each other. And so then there's going to be a trig substitution. It's cosine of those 2 pieces plus each other and a cosine of those 2 pieces minus each other. But the nice thing is they're separated. Now it's the difference between cosines, and I can integrate a single cosine. I just can't figure out how to integrate 2 sines multiplied by each other. Okay, so this trig substitution simplifies things. Okay, and then we can take the integral of that cosine. Okay, let's simplify a little bit. Let's pull this x out. So we have an x here and an x here. So let's combine these 2 pieces with x. Okay, so that's right there. We have the n prime pi minus n pi all over L. And then we got this phase shift piece. And then let's do the same thing here. So this piece goes here and that piece comes down because they're both a function of x. And that'll help us pull those pieces out when we take the integral. Okay, so now I think we're ready to integrate. So we end up with the integral of cosine being sine, and we pulled whatever's in front of x, we inverted it and pulled it out front. Now where'd my L go? Well, out front I have a 1 over L, so it canceled. So we just have this 1 over n pi piece, and then we did the same thing over here. I took this piece in front of x, pulled it out, inverted it, and multiplied by 1 over L, so the L's are gone, and I have this piece. Then we evaluate that at L and minus L over 2. And we end up with integer multiples of pi again inside the sine function. So if my integers are, if my quantum numbers are integers, then the difference between integers is also going to be an integer. You can prove that to yourself. Just think about 4,506 minus 6. Okay, I got another integer. So this is great. So no matter what it is, it's going to be the sign of an integer multiple of pi. And so 0 here, 0 there, 0 there, 0 there, everything equals 0. So no matter what difference I have in my quantum states, they're all going to be 0 when integrated over all space. So that's great. That's called orthogonality. So if n and n prime are different, the result is 0. If n and n prime are the same, the result is 1. So our wave functions are both normalized and orthogonal. So that's beautiful. Now let's get into the observables. We'll solve the Schrodinger equation to get our energies, because our energies are observable, at least in differences. So for every measurable property, there's an operator in quantum mechanics. So if you do an experiment in the lab, like absorption, there should be a way to simulate that with the operator. Here's some of the operators. If you want to calculate the momentum of a wave function, this is the operator. If you want to calculate the kinetic energy of the operator, you have this, h bar squared over 2m, and the second derivative. So this part's the kinetic energy. The potential energy is going to depend upon the system, and so the total energy is the kinetic plus the potential energy. So you see this piece comes down here, this piece goes there. The position operator is x. So if this is all in one dimension, it's the x-axis. And we're using the x-axis to simulate the electric dipole moment in light. But you could also kind of think of it as in terms of like a photon. Photon light coming in and hitting our wave function. Are they going to hit? Well, a way to simulate the position of our wave function that's going to be hit by the photon is to multiply it by x. So multiply that wave function by x is a way to calculate the position of that particle. So we have these, when we operate on this, we can simulate that measurement by using an eigenvalue, eigenvector equation. So the properties of the wave function and the operator will cause the system to be quantized. And these eigenvalues are the quantized observables. So we'll let you finish the box there. So let's do this. Let's solve the Schrodinger equation and get our energies. So this is the eigenvalue equation, the Schrodinger equation. Notice it's a strange equation. We have h times psi, or operating on psi, is equal to E psi. So notice how the wave function, you operate on the wave function, and then you get it back. So that's why we need functions that you can take the second derivative of, and the function's not changed. So you start out with sine, you take the first derivative, you get a cosine, you take the second derivative, you get minus sine, but sine is back. So this makes it a good wave function to use with the second derivative operator. So here's the Schrodinger equation with our wave function put in. We have just the kinetic energy operator here. And we have the second derivative piece, and we're going to focus on taking the second derivative of sine and then pulling out the stuff that's in front of x. Now we're taking derivatives this time, so we don't flip it upside down. So we only do that with the integral. And we leave the right side unchanged. Because what's going to happen is we're going to take the first derivative and some stuff's going to come out. And we're going to take the second derivative and more stuff's going to come out. And that stuff that came out will be the energies. I say, so by comparison, we can operate, and once we're done with all the integrals and all the derivatives and everything that the operator is telling us to do, we have constants on both sides. And those constants are multiplied by our wave function. So by inspection, you can make the constants equal to each other. We have a constant on the right that's E of n. The constants on the left will be what equals E of n. So here we have it. We're going to take the first derivative. And we did that. Now we have the second derivative sitting here. We pull the n pi over L out. And we get cosine. Now we're going to take the derivative of cosine. And we get minus sine. So where's the minus sign? Well, it canceled this guy. So when we take the the cosine to sine, we get a -1. Why did I do a plus? We get a -1. Okay, so we end up with plus sign. And we bring out those pieces again, the n pi over L. And now we have that squared. And we get our wave function back. So this is psi. This is psi. So by inspection, we see that energy is equal to this piece right here. Now remember, h bar is h over 2 pi squared. So we're going to have a pi squared here and a pi squared here. So the pi's are going to cancel. And this 2 becomes a 4, and 4 times 2 is 8. So that's where the 8 came from. We lost the pi, we lost the bar on the h, and we have 8 in the bottom all of a sudden. We still have the mass, we have the bond length squared, and the quantum number squared. So this is the analytical solution to the Schrodinger equation, and these are the 1D particle in a box energies that we have. So this is the sort of the literature value, or the theoretical value for the particle in a box energy levels. We're going to calculate this in your projects, your Excel projects, numerically. And they're going to match really well, except at the higher quantum numbers. So that's one of the questions out of that project, is why don't the higher quantum numbers match the analytical energies well? So I'll let you chew on that when you get there. Okay. Now we could do this with other observables, and we would call it the expectation value. So let's get this from the Schrodinger equation. If we were to take the Schrodinger equation, h psi equals E psi, and left multiply by the wave function, really the complex conjugate of that wave function, and integrate over all space, this E is a constant. And so it could come out front, and we would have this psi. And then we could move this over to the denominator, to the other side. And so we can see now that the expectation value for E is equal to this piece right here. So this is essentially the Schrodinger equation in integral form. So this is postulate 4. We can use expectation values to simulate these experimental values. So the Hamiltonian operator, we did that. If we do that with state 1, we get E1. If we do that with state 2, we get E2, 3, 4, and so on. For terms of spectroscopy, the spectral lines are differences between energy levels. And so this transition equation, delta E, would be the energy difference between two energy levels. And so that would be the Schrodinger equation. I'm just showing you how the wave functions figure into this delta E. They're in the horizontal axis of the spectrum based upon our energies. So let's do this for a general case. Anytime we want to know particular transitions, we've got to figure out the differences, these energy differences in our energy level diagram. We know those analytical energies now, and we could solve this for a delta n. So if this was 1 to 2, delta n equals 1, right? We went up by 1. What if it was 1 to 3? It would be delta n equals 2. 1 to 4 would be delta n equals 3, and so on. So we could solve this for a general case by just putting delta n in here. So this is the general solution. Notice it's nice, all these constants come out front, h bar, 8ml squared, and so on. So we'll pull all those out, and we got this nice little polynomial equation. We could solve that. I haven't skipped any steps. I've got n squared minus n squared, and so these guys cancel. and we end up with N. So I went ahead and I pulled a delta N out to get it in this form. So we have delta N out front. We've got this constant, and then we have N plus delta N over 2. And this is our transition equation for all delta N's. Now that's in energy. That would be where the peaks show up if our x-axis or horizontal axis in spectroscopy was energy. But a lot of times our horizontal axis is frequency or wavelength. So we could convert this to frequency by dividing that energy by Planck's constant. So E equals h nu, and so nu is equal to E over h. And so you can verify that we've lost a square, right? We've divided by h, so we've lost a square. And that's the transition equation in terms of frequency. What about wavelength? Well, E equals hc over lambda, and so lambda is equal to hc over E. So notice we've inverted everything. We've lost the h squared, and we've gained a c on top. Okay. So this is the general solution for all transitions for particle in a box plotted in terms of wavelength. So if we're doing delta n equals 1, you put in 1 for all your delta n's, and you've got now for quantum state 1 to 2 here, 2 to 3, 3 to 4, and you can plot out your peaks. So this is the general transition equations for all delta n. Time dependence. We're not going to deal with this, but that's postulate 5. All right. So we have essentially the change in time is another way to think of it. This momentum in position, but we could do the sort of the momentum in time. What's happening to the wave function with respect to time? And when we add that in, we end up with, an Euler relationship, e to the minus it. And so we end up with oscillatory functions, cosine and sine times I. And it's a way to think about these wave functions. They don't just go up and down. What we're plotting is the real plane. There's also an imaginary plane, and so they can be going circular. So they go from real plus 1 to imaginary plus 1, and negative real, negative imaginary. So in time, there's always an imaginary component. Okay, we did it. I didn't know if we were going to finish. I kept looking at the clock over here. So we got time for some questions. Anything in here that you just thought, okay, I need him to clarify? Yes? No, but that you've got it, me talking in class, and then you got the video. So yes, it is on. So. Okay, have you got the Blackboard site? Are you? Yeah. So I'll put the playlist on an announcement today, so we'll be able to find it very easily. Okay. 18. I don't know where the numbers are. Tell me when to stop. Am I getting warm? Postulate 3. Oh, right here? Yes. Yeah, sure. Excellent. All right, y'all have a safe 3-day weekend. Okay. See you Wednesday.